Hello, I'm Ali. Welcome to this course. This is the first course in the Intermediate Mathematics series by Swiss Lecture. In this video, we'll be dealing with the concept of finite and infinite sets. But first, let's have a quick recap to refresh our memories. Then we'll move on to discuss intervals in set theory. Finally, in the third part, we'll be introduced to the notion of finite and infinite sets. First of all, I want you to think of a set as a group of numbers. For example, here I have a set of 5 numbers. And when dealing with numbers, one of the first things that piques interest is whether a number belongs to a set or not. It's like making a team of numbers and we're figuring out who's on the team. Now let's call my set A, and if I pick a number 1, it's in set A, but if I choose 25, for example, it's not in my set. Just keep an eye on the symbols used in mathematics for these kind of relationships. Now let's explore some important and well-known sets of numbers. We'll begin with the numbers you first learned in your early years. These are the natural numbers starting from 1 and going on forever. Now, by including 0, the set transforms into another set known as whole numbers. Therefore, whole numbers include all the members of natural numbers along with the addition of 0. By taking all the members of the set of whole numbers and including negative numbers, we expand to a larger set known as integers. And now let's dive into the world of rational numbers. These are special numbers that can be expressed as fractions, like for example 3/4 or minus 2/5. In simpler terms, any number you can write as a fraction, where the numerator is an integer and the denominator is a non-zero integer, is a rational number. Moving on to irrational numbers, these are a bit different. Unlike rational numbers, irrational numbers cannot be expressed as fractions. They are numbers like the square root of 2 or pi, which go on forever without repeating in decimal form. As we learn about irrational numbers, let's also meet a new symbol, the subset. Think of it like a family tree for numbers. We have natural numbers, then whole numbers, then integers, and finally integers are a part of rational numbers. But there is the interesting part: there is no family connection between these sets and the group of irrational numbers. Now, on a different note, when we combine rational numbers or Q with their cousins called irrational numbers, we create the big family of real numbers. It's like bringing together two big groups to form an even bigger one, which is called the real number set. We can do also some cool stuff with sets, like combining them in different ways. Let's talk about three operations: union, intersection, and difference. To do that, imagine two sets A and B. When we put all the numbers that are in either A or B or both, we call it the union of the sets. To write the union set of A and B, just list all the numbers from both sets without writing the same number twice. And there is also something else cool called the intersection. It's like finding the common friends in two groups. The intersection set has all the numbers that are in both sets, so it's called a special group of numbers that both sets have in common. And finally, if we have two groups A and B, we can find something called the difference. A subtract B is like looking at the numbers that are only in A, not in B. On the other hand, B subtract A is the set of numbers that are only in B, not in A. It's like figuring out what makes each group unique. Now, let's tackle this exercise and pay close attention to how I apply the mentioned principles to solve it. To create the union set, I list all the members, making sure not to repeat any member that appears in both sets. In this case, 2. I write it just once. And to form the intersection set, I chose only the numbers that are common to both sets. In this case, again, 2. I pick up only this number. For the difference set, I select only the members from set A for A subtract B, excluding the ones from set B, and vice versa for B subtract A, where I choose only the members from set B, leaving out the ones from set A. And here, one more exercise. Just remember, when one set is a subset of the other, the union of both sets is always the larger one, and the intersection set is always the smaller set. It's like fitting puzzle, if you want, pieces together. The union gives us a bigger picture, and the intersection focuses on what they have in common. And when dealing with the difference of two sets, if you subtract a smaller set from a larger one, as you can see in the third example here, it leaves you with an empty set. It's like taking away everything that was shared between them. We write the set representation of this range like this. If we only want the real numbers between 0 and 1 but not including 0 and 1, we say open interval from 0 to 1. Remember, parentheses are used to indicate open intervals on either side of the interval. Inequalities provide another method for representing intervals. Think about the real numbers from 0 to 1, as in this exercise. In this range, you have numbers like 0.5, 0.2, square root of 2 over 2, and more. And now let's look at the representation on the real number line. Here we mark 0 and 1 with hollow circles because they are excluded as per the exercise requirements. However, all the real numbers between 0 and 1 are included in this representation. Now, in this exercise, we are doing something different. Unlike the previous example, here we are working with a closed interval between the same numbers as before. Compare this exercise with the previous one. As the interval is closed, round brackets are replaced by square brackets. Smaller than or greater than symbols are replaced by smaller than or equal and greater than or equal symbols. And the distinction on the real number line representation lies in using solid circles instead of hollow circles. Solid circles indicate that the numbers are included in the interval. Attention! Half open and half closed are two different terms for the same type of interval. Any half open interval is inherently half closed at the same time. Up to this point, we've only dealt with bounded sets, whether the interval was open or closed from either side. Now we move on to unbounded intervals. This means an open interval on one side or both sides, where the open side's limit approaches infinity. In this exercise, the interval includes all the real numbers greater than a. In this part of the exercise, you encounter an interval unbounded from the right and closed from the left side. This means that interval includes all numbers greater than or equal to a. Let's remember the union set of two sets is that combination of all unique elements from both sets. In this case, the union set would include all numbers that are in set A, set B, or both. The left limit of the union interval does not include -1, as it's not present in either set A or set B. The intersection set of two sets contains the members that are present in both sets. In this case, only the number 1 is common to both sets, while the number 2 is exclusively a member of set B. In subtraction A minus B contains only the members that are exclusive to interval A. Therefore, it does not include the number -1 or 1, as -1 does not exist in interval A, and A is a common member between the two intervals. This is a fascinating exercise. The first interval is the union of two intervals. What we aim to find is the intersection of this union with the interval B. Consider the set A. It has three members. So the cardinality of the set A is equal to 3. Now take another set B. Its members are 1, 2, 3, 4, and go on to infinity. The set C has 0 members. It's an empty set. It's clear that the number of the members of the set B cannot be expressed by a whole number. It's an example of an infinite set.